Welcome, everybody, to our Tech Talk series. My name is Jeffrey Greenblatt in google.org, and we're very pleased to have today Sally Benson from Stanford University to come and talk with us about carbon sequestration and capture from power plants. Wanted to give you a few brief highlights on Sally's background. She currently serves as Executive Director of the Global Climate and Energy Project, where she has been at Stanford since last March. Previously, she was at LBL, Lawrence Berkeley Lab, in various management positions, including Deputy Director of Operations and Division Director for Earth Sciences. She had several scientific foci while at LBL, including primarily geologic storage of CO2 in deep underground formations, but also looking at technologies and energy systems for bringing about a low-carbon future and the influence of climate change on critical habitats, as well as geotechnical instrumentation. Sally got her BS in geology from Columbia University in 1977 and her master's and PhD in materials science and mineral engineering from UC Berkeley. She's also the author or co-author of over 160 scientific publications. Now, I first met Sally when she came to give a lecture at Princeton, I believe, where I was a few years ago, just learning about climate change science, and particularly this novel idea at the time for putting large amounts of CO2 underground in order to keep it out of the atmosphere, part of the program I was involved in called the Carbon Mitigation Initiative. And since then, we've crossed paths several times at scientific conferences, and now that we both live in the Bay Area, occasionally in cafes. So please help me welcome Sally here. Thank you.
Great. Well, anyway, thanks a lot. So are we all ready to go? And yeah, okay. All right, so I'm going to be talking about carbon dioxide capture and sequestration, or sometimes called carbon dioxide capture and storage. And you'll notice I chose sort of a provocative title, Hype or Hope. And that is because I think there's a lot of diverse opinions about carbon dioxide capture and storage. And I think it's really good to recognize both sides of the discussion. And what I'll try to do is elucidate what I think are some of the issues on both sides, but finally give you my opinion about hype or hope, or somewhere in between that. So what about hope? Why are people hopeful? Well, there's sort of a list. These are the kind of things you hear that studies, integrated assessment studies, say that 20% of the needed emissions reductions could be achieved over the next 100 years using CCS. You also hear things like, if you do CCS, it makes the overall mitigation effort to reduce greenhouse gases less expensive if you do this. So that's one thing you hear. The other thing is you hear sort of the hopeful, well, wow, if we can't make this work, if CCS doesn't work, we're really in trouble because we use so many fossil fuels and we rely so heavily on coal, primarily for electricity. So, and particularly in the developing world, there's a lot of growing reliance on fossil fuels. So there's that kind of hope. Other arguments are that basically that all the sort of toolkit of things that we need to do for CCS are available today. There's no real new technology needed, that it's just we need to put them together in a unique way that's never happened before on this scale. There's also the view that, well, we've been injecting CO2 or other fluids in oil fields for more than 30 years. So basically, there's nothing new on the storage side, and so you hear that. And then you get the, well, let's just do it. This is such a serious problem dealing with climate change that let's just go do this. So these are the kind of hopeful arguments that you hear. And then on the other side, sort of the hype, a lot of concern that CCS is really expensive and, just never going to do it. And forget it. So you also hear a lot of discussion about the environmental risk being unacceptably high, and that we're going to have disastrous situations where whole towns are going to be wiped out and so forth. There's also the argument that, well, whatever CO2 you put underground, it's just going to leak back into the atmosphere, so what's the purpose of doing it in the first place? And then there are other arguments that the institutional barriers are just too high. And particularly in that context, I think people are thinking about public acceptance, that there are analogous kinds of waste disposal operations that people just don't like, and therefore it will be too difficult. So this doesn't represent the full spectrum of opinions, but it kind of lays the ground for both sides of this. So when we come to the end of this talk, I'll give you my opinions on these. And anyway, as we go along, also if you have questions, let me know. So to answer this question about the potential role it will play, I think there are a number of key questions, and this isn't a complete list, but I think these are some of the heavy hitters. So the first one is capture technically feasible. Can we do this? Can we capture CO2 from the flue gases or smokestacks of power plants? Another big one is, will CO2 leak back to the surface? Is putting this underground futile, or in fact, will it stay where we put it? Another key question is, will CO2 storage create unacceptable environmental hazards? So that if we do this, that maybe it doesn't leak out, but it damages groundwater, as an example. Another one is there enough storage capacity? Say everything else works fine, it's cost effective, but is there simply enough pore space underground to do this? Another one, will CCS be too costly to implement? Is the cost of electricity generation, including capture and storage, just cost prohibitive, and therefore we'll never do it? And then finally, a key question, are there some non-technical issues or institutional issues or societal issues that would impede deployment? So I'll hopefully answer these questions and then go back again and sort of try to lay out the hype versus hope with regard to these. So now to get to the technology we're talking about, carbon dioxide capture and storage. It basically involves taking the carbon dioxide, instead of allowing it freely to be emitted to the atmosphere, that we would somehow capture it, and that we would then compress it to a liquid form. Basically, it becomes a liquid. And then we put it in pipelines, or we could put it on ships and transport it someplace where we could inject it deep underground for essentially permanent storage. So this is basically the scheme that is involved in this technology. And I'll talk about each of these components. And we'll start with capture. So answering the question, can we capture carbon dioxide? So there are a number of different options for doing this, and they're illustrated here on this chart. And let's, for the moment, focus on electricity production. And this is the primary focus of the target of carbon dioxide capture and storage, is electricity production, and primarily coal-based electricity production, which is today about 50% of all the electricity used comes from coal in this country. So there are three different approaches that you can use. The first is something called post-combustion capture. And basically what you would do is you would run your power plant just like we run it today. You take fossil fuels and you mix it with air, which is mostly nitrogen, and that after you've burned the fossil fuels, that you would then put in some kind of chemical separation process that would separate the carbon dioxide from nitrogen. So that's the post-combustion challenge. So that's one approach to do that, and I'll talk about some of the pluses and minuses of that in a minute. So that would be something that we could use on power plants that we have today. The second choice is something called pre-combustion capture, and here what you do is that instead of burning coal in air, for example, that you instead first convert the coal to a gas. Something called a synthesis gas, which is typically a mixture of carbon monoxide and hydrogen. You also have the choice to do a further chemical reaction that gets rid of all the carbon monoxide, and by reacting it with water with a catalyst present, and that produces then a pure hydrogen stream and a pure CO2 stream. So that's pre-combustion capture, and what's good about that is that now your separations job is somewhat simpler, as you're just separating carbon dioxide from hydrogen, or carbon dioxide from carbon monoxide and hydrogen, and typically the CO2 concentrations are much higher than you would have in a post-combustion plant where you're trying to separate carbon dioxide from nitrogen. So the rule of thumb is the more concentrated the CO2 in the waste stream, the easier it is to capture. Anyway, so pre-combustion is the second one. Basically, though, a completely different kind of power plant than we run today. And then the final one is something called oxy-fuel combustion. And the idea here is that instead of burning a fossil fuel, be it natural gas or coal, in air, which has got a lot of nitrogen, that you separate the oxygen, which is the reactant that you really want, from air. And so you're separating nitrogen from oxygen. And then you do your combustion in basically a pure oxygen environment. And then the waste product from that is a mixture of basically carbon dioxide and water. There are contaminants present, but those can be cleaned up. But basically, you have a waste stream of carbon dioxide and water. So that one is a technology that is, in principle, rather straightforward, but it hasn't been used today, and there are challenges associated with the very high temperatures and needing to moderate the temperatures, because you would have very, very hot conditions with oxygen combustion alone. So these are the three approaches that are available today. To one degree or another, we have experience with all of them, though the post-combustion technology would be the one that is most mature amongst these. So that's on the power plant side. There's also, I think, an oft-forgotten issue that actually CCS in the long run might be very important for, and that has to do with manufacturing. About 25% of our emissions are from manufacturing. This is likely to grow in the future as greater development takes place across the world. And right now, we don't really have a good pathway for eliminating a lot of those emissions. And post-combustion capture or oxygen combustion may provide an option for industrial emissions. Okay, so those are the options. So we can then go down the list and look at the technology and some of the advantages and disadvantages or drawbacks. So post-combustion technology, it's basically a mature technology. It's used at scale today, not for this application primarily. It's used more in gas processing. When natural gas is produced, it often has a lot of CO2 in it. So this exact same technology is used. It's basically a chemical separation where you contact the gas with a liquid. The liquid absorbs the carbon dioxide. You then take that liquid aside and heat it back up, and the CO2 is released. So anyway, well, a very established technology. It's also used today in things like when we buy soft drinks, for example. Most of the CO2 is produced by this post-combustion type of capture. It would be a standard retrofit to a typical power plant, but it's not that simple. I mean, these are very, very big facilities. So to retrofit a plant, you might need real estate of maybe as much as 6 acres or so for a big power plant. But in principle, it's a standard retrofit. In terms of drawbacks, first thing is it's got a high energy penalty, meaning it takes a lot of energy to do the capture. The primary energy requirement is in this stage where you have the liquid that's got CO2 dissolved in it, and you need to heat it up to release the CO2. That takes a lot of energy with the kind of solvents that are available today. So you could have an energy penalty, or sort of a hit, right off the board of about 30%. And obviously, that's a lot. So at the very least, it's sort of wasteful. Second thing is that the cost is comparatively high. And it's not something that you would do today unless there were policies to limit carbon emissions. And we'll talk more about the cost later. Okay, so pre-combustion technology, also sometimes called IGCC, Integrated Gasification Combined Cycle. That's probably what you hear about it in the newspapers. There are studies which suggest that on a per ton of CO2 basis, it's going to be less expensive than the post-combustion capture, though, frankly, I think that's really debatable. Probably most importantly is that the energy penalties are lower. They're only on the order of 10 to 15%. I mean, still, that's still a pretty big number, but it's certainly not as high as 30%. Another benefit is that when you go through the gasification process, you're basically producing hydrogen. And so you could imagine hybrid plants that both provide hydrogen for power generation, but also hydrogen for other possible applications, such as vehicle transportation or as a chemical feedstock. So then in terms of drawbacks, there are some significant ones. Basically, if you look at power producers today, they know how to burn things, and they know how to make steam, and they know how to run steam through a turbine, or they know how to run a gas turbine. They're fairly simple operations. IGCC is basically a very complicated chemical process. So the workforce that is in place today to kind of run these facilities is quite a different workforce than you'd need to run a complex chemical plant. It's much more akin to running a refinery than it is to running a power generation station. And there's a lot of concern on the part of the companies, the power generation companies, to all of a sudden be faced with a system that they know less about. And there are lots of issues about reliability. That's one of the key things. In our electricity sector, we like reliability. We like cheap and reliable. And so you bring in a completely new technology, and it creates a lot of concerns on both of those sides. So another thing is that if you move to pre-combustion capture, that or IGCC, you basically have to start from scratch. I mean, you might have the real estate for your power plant, but basically you'd need to pull out what you had there and replace it with something new, or repowering, and that would take a very large capital investment to do that. Also, IGCC plants tend to be more expensive on a per megawatt basis, for example, than a standard pulverized coal type plant, or certainly much more expensive than a natural gas combined cycle plant. So then finally moving to oxygen combustion, the real advantage is that the separation at the downstream end is very straightforward. You have a concentrated source of CO2. The other primary constituent is water, and that's a pretty easy separation to do. And this would lead to potentially higher generation efficiencies. However, if you're doing oxygen combustion, you have to separate oxygen from air. And that's quite an energy-intensive process as well. So even though on a generation side you can be more efficient, you still have the inefficiency of separating oxygen from air. In terms of some of the drawbacks, new materials may be required for the higher temperature environments. Again, I mentioned the oxygen separation, which is costly and energy intensive. And again, it's not a standard retrofit. You couldn't just take away the air and put oxygen there. You'd need to change your materials. So, okay, so these are the advantages and drawbacks of each of these. So I think at this point we will kind of come to the end of the capture discussion, and at the very end I'll talk about costs of the integrated capture and storage system. So in terms of the other components in this chain, compression, pipeline transportation, all of that is straightforward. It's done today for CO2, for things like CO2, so no big deal there. Really the issue is underground injection, and doing this at a scale that would make a difference. So the first question is well, where would we consider putting the CO2? And there are three main kind of rocks. There are igneous rocks. Those are like granite, like think Sierra Nevada. There are volcanic rocks, think Hawaii, big black thick rocks with vesicles in it. And then the third main type of rock are sedimentary rocks. And those are things like the rocks you can see in the Great Central Valley, or if you're driving to Tahoe, there are a lot of sedimentary rocks along the roadside there. And those basically form as mountains are eroded, and the sediments are transported down into valleys, and eventually it fills up, and that's what sedimentary rocks are. So in terms of CO2 storage, sedimentary rocks are the only place that today are being seriously considered for CO2 storage. The other type of rocks, though, are interesting research opportunities. Much, much less is known about those. So the question then is, where are those sedimentary basins that might be potential sequestration opportunities? And they're shown by this map up here on the left-hand side. And you'll notice sort of three colors. There's the darkest gray, and those are places where there are sedimentary basins that are considered to be highly prospective for storage, meaning if you went and looked there, you'd likely be able to find some place to put CO2. They're the sort of medium gray colors, and those are areas where there's a sedimentary basin, but maybe it's not deep enough, or maybe it doesn't have the right kind of layer cake geology that you'd need to store CO2. But nevertheless, there's sedimentary basins where you could take a look. It also might just be areas where we don't know very much about. And then there are on the continents, there are the white kind of areas, and those are areas where we don't have the right types of rocks, that they are igneous rocks or they're metamorphic rocks. Okay, so actually, I didn't ever describe what metamorphic rocks are. Metamorphic rocks are basically either igneous or sedimentary rocks that have been cooked at great depths below the Earth's crust, and they tend to be very hard and typically fractured if they have any permeability at all. Okay, so those are in general, the areas. So what does a sedimentary basin look like? Well, one of them is illustrated on the right-hand panel here, and this is actually a sedimentary basin in California. This is actually quite close to us, a cross-section running pretty much through Sacramento. And you'll notice there are two main colors there. There's sort of a yellow color, and those represent sands. So those are sediments that are deposited by things like rivers and streams, sort of high-energy deposits where you're carrying along fairly big grains that are eroding, and then they fall out into the bottom of the valley. And those are the places we might store CO2. And the other color you see are the gray colors. And those are sediments that are laid down like in a really deep lake or in the ocean. And those are very low energy environments, so they tend to have very, very, very tiny clay particles that are laid down and compacted and are very, very low permeability. It's very difficult to push any fluids through those. So those gray kind of areas act like the seals. Yeah?
I had asked this question because it jumps out of the map. The two projected largest producers of CO2 don't seem to have prospective.
Right, India. India is...
The coast of China or India?
Yeah, so India in particular is, much of it is basaltic rock. So it really is not a lot of capacity there. There is some capacity offshore of India to the west. China is in a little bit better situation. There are some sedimentary basins onshore and offshore, and at the time this map was developed, there had been no serious assessment of China's storage capacity. Since then, one study has been done, and basically it's said that it's sort of on par with the North American capacity. I think it's really too early to tell. I think that there's a lot of work that needs to be done in China. It certainly isn't going to be giant. It's not going to be the Middle East of storage capacity. It will always be a more challenging place than for example, the former Soviet Union, which has also got a lot of storage capacity. Okay, so these are the kind of places we can put CO2. So that's sort of the big picture, but then we need to look at specific formations that we would inject them in. And the most obvious is oil and gas reservoirs. Oil and gas reservoirs are in sedimentary basins, and those are places where over geologic time frames of millions and millions of years, fluids, buoyant fluids, gases or oil, which is buoyant compared to, or less dense compared to water, that those got trapped. And so what's good about that is we know that there was a seal that sort of stood the test of geologic time. And in addition, that some fraction of what had been in the pore spaces, oil or gas, has been removed, conceivably making room for some CO2. So that's kind of the most obvious because they both have seals and they're partially depleted. So the second option is really a variant on that, and that is that you combine the storage activity with continued production, or enhanced oil production, or enhanced gas production. And so basically, while you're injecting CO2, you continue to extract oil or gas. And so you do the two operations at the same time, and then eventually you'd stop producing oil or gas, and then you'd just try to fill it up the rest of the way with CO2. Benefit of that is that there's commercial interest in that there are oil field operators who would be happy to have the CO2 because they can produce more oil. And what it allows you to do is make that operation more cost effective, because you basically now have a market for the CO2 as opposed to the CO2 really being considered as a waste. So those are the first two options. The next is to put CO2 in what are called deep saline formations. So basically what you want to look for is like an oil reservoir, so a place that's got a seal, and it's got the porous, sandy storage zone underneath it, but it's not filled with oil. It's just filled with very salty water that is isolated from the sort of hydrosphere that has active circulation of fluids in the crust. So that's saline formations. And then the final one is that CO2 can be put into coal beds, and the storage mechanism is somewhat different. The CO2 actually absorbs to the surfaces of the coal and becomes basically part of the coal itself. And that option is much less well developed than the other two. Okay, so those are the kind of places that we can put it. So I think the definitive work on CO2 capture and storage, which was published in 2005, and basically is still very current. So those of you who have a real interest in this, there's 800 or 900 pages of detail on the things that I'm talking about. It also covers things like ocean storage and so forth. Anyway, so there's a very good reference book on this. But what I wanted to do is talk about two of the important conclusions about the storage, the security of storage. You know, basically, will it leak, and will it create unacceptable environmental problems? And I'll say these two conclusions, and then I'll spend a whole bunch of time trying to explain why this group concluded this. The people who worked on geologic storage, there were 23 lead authors from around the world and about 7 contributing authors, all involved in one aspect or the other of this. Okay, so to kind of cut to the chase is that the first quote that's relevant is that observations from engineered and natural analogs, as well as models, suggest that the refraction retained in appropriately selected and managed geological reservoirs is likely to exceed 99% over 100 years, or actually it's very likely to exceed 99% over 100 years, and is likely to exceed 99% over 1,000 years. So basically this was a statement about the confidence that if you did everything right, that you should be able to achieve good performance, or that all systems aren't naturally leaky. So that was that sense. And then the second one had to do with the environmental impacts. And basically it had the same kind of list of caveats, like you have to do everything right. But if you do everything right, and you plug leaks if they find them, or you remediate leaks, that the local health, safety, and environmental risks of geological storage would be comparable to the risks of current activities such as natural gas storage, enhanced oil recovery, deep underground disposal of acid gas. So basically this, so one, CO2 stays underground, can stay underground for a long time, and second, it's not a particularly unique activity compared to the whole range of activities we did today. Okay, so now what I want to do is sort of describe why the group concluded this. So the first thing has to do with natural analogs for CO2 storage. So these are things that are found in nature that give you sort of a proof in principle that CO2 or buoyant fluids can be trapped underground. We've already talked about the first of them, oil and gas reservoirs. Natural gas has about half the density of CO2, meaning it's even more buoyant. Oil is a little bit more dense, but not much more dense than CO2 would be at those kind of conditions. And we have proof that those fluids stay trapped for millions and millions of years. Now, that's not to say there aren't some oil and gas reservoirs that leak. They do. But there are many of them that don't leak. And the worldwide sort of leakage rate from these systems, as estimated by marine environments, is like 10 to the minus 7 So 1 part in 10 to the 7 leaks per year. So extremely high retention rates. Okay, the second thing is about CO2 itself. So you might say, okay, well, oil and gas, well, fine. Maybe they have unique chemical composition, doesn't react with the rocks, and therefore CO2 could be different. Well, it turns out that there are also natural CO2 reservoirs that are present. It also turns out that many oil and gas reservoirs also have a lot of CO2 in them. So it doesn't look like there's anything special about CO2 that makes it more likely to leak. So these natural analogs are proof in principle that you could store CO2 underground for very long time periods. The second part has to do with what were called industrial analogs. So these are operations that we carry out today or over the past century that are somehow analogous with CO2 storage or inform safety and longevity issue. So the first of them is CO2 enhanced oil recovery. This is actually a technology that was developed in the 80s, late 70s and 80s. CO2 is injected into oil reservoirs. It's miscible with the oil, and it makes it much easier to get the oil out. So there's a great deal of experience with that, most of it in the United States. And this little map shows a picture of all the gray areas where CO2 enhanced oil recovery is practiced today, and then these little red areas where there are natural CO2 reservoirs that are actually used to provide CO2 for these injections. So most of the CO2 that's injected is actually CO2 that's been extracted from a natural reservoir and put into the oil field. And basically these projects are carried out safely within the range of environmental regulations that are imposed on a state-by-state basis. Second one is natural gas storage. We've practiced natural gas storage for over 100 years. There's a very large natural gas storage field not very far from us, McDonald Island. If you drive through the Delta, you're driving right on top of a very huge natural gas storage field, and it's developed to provide gas to San Francisco in the wintertime because you need a lot of gas. People are using it for heating and so forth. And again, very safe. You can go visit the project. It's actually quite interesting. And I'll show you some maps. And then finally, something called acid gas disposal. This is something that's done in Canada. Mixtures of SO2 and CO2 and sometimes H2S are injected underground. Again, no problems, though this area is far less monitored than the other two things that I've talked about so far. Okay, so what these industrial, yes?
Have there ever been any incidents of large-scale release that threaten animal life or
From natural gas storage projects, so there are two types of natural gas storage projects. One are done like in saline aquifers or oil and gas reservoirs, natural geologic formations. There are also projects that are done in salt caverns that are mined. The salt cavern projects, if you get a leak in the well casing, you can have a very rapid release. And there have been some bad examples of leaks associated with that. There was a town in Hutchinson, Kansas. If you Google Hutchinson, Kansas, you can find examples. I don't think anyone was hurt, but there was fire, at the land surface, things you wouldn't want to happen. In Illinois, there was an early example of a natural gas storage project that was leaking, and it ended up making an explosion in somebody's outhouse. So there are examples, but by and large, as the regulations improved, it's gotten safer and safer, and now there are very, very few incidents. Okay, so anyway, so then the final example is there are real storage projects today. There are 20-plus cumulative years of experience between the Schleifner project, Weyburn project, and Insala project, which I'll describe to you right now. But just really quickly, here's a map showing the location of natural gas storage projects in Europe and in the United States. And you can see there are many of them. There are over 450 in the United States alone, and fairly broadly distributed. So that's that. Okay, so the real projects. So Schleifner project, this is offshore Norway. And you can see the platform here. This is the capture facility. This is a natural gas processing facility. So they produce natural gas from this platform. It's got too much CO2 in it. They need to strip it off, which they do here. This is exactly the kind of post-combustion unit you'd use in a power plant. And okay, so back in the mid-90s, they wanted to produce this gas. The Norwegian government had a policy: if you have offshore CO2 emissions, that you have to pay a tax. It was about $50 a ton. So they decided it would be cheaper to actually put it underground. And I think they also had some foresight that this may become a very important technology. So, so what they do is they take the CO2 that's separated from that facility there, and they inject it into a subsea aquifer, illustrated by that blue layer there. And they've now been doing that for about 12 years. And they inject about 1 million tons a year. So that's about 1/5 of the size for a very large-scale power plant in the United States. So it's not as big, but it's not orders of magnitude off. So it's sort of industrially relevant scale. It might be that we probably never inject more than 1 million tons per year into any individual well. So in many ways, this is a good analog to what a commercial scale power plant operation might be. So there's that project. Basically, it's gone great. Another project is the Weyburn project. This is in Canada. They take CO2 that's produced from a syngas facility in North Dakota, pipeline of nearly 300 miles up into Canada. And here they inject the CO2, about 1.7 million tons per year on average, into an oil field. Again, this project has gone fine. Both of the last two projects have had lots of monitoring, and I'll show you some of the data from Schleifner as we go along. No evidence for leakage out of those projects. And the final one is a project in Algeria. This one is done by BP and Sonatrach. Sonatrach's the national oil company of Algeria. Statoil recently became a partner also. This is another gas field where they produce gas. They have to strip out the CO2. Here you can see that very large facility. So these gas separation facilities are really large. They take that CO2 and they inject it actually back into the gas field, but they inject it into the water-filled part of the gas field. So the gas usually just occupies the very little top part. So they're injecting CO2 down here. Eventually, they expect it to flow back into the gas field. This has been a very challenging project. It's a difficult place to work, much higher injection pressures, and a very low permeability formation. So a good analog to a more challenging setting for this kind of project. So these are the real projects. So I want to move on now to talk about some of the caveats that I mentioned. That when the IPCC concluded that it could be 99% retention, there were all the ifs. If you do this right and if you do this right. Well, this is basically the list. At the foundation is we have to really understand the storage mechanisms and leakage mechanisms. We need to learn how to select sites so that they have good seals and that they provide good storage reservoirs. We need to have storage engineering, that you're not just going to go, drill a hole in the ground and start pumping CO2 in. Like oil and gas field production operations, this will be evolved to be a complex science of optimization primarily. Safe operations, lots of experience with that, but that'll be very important. Monitoring will be a key component. I'll say more about that. Remediation plans. You have to have a backup plan. If something goes wrong, you've got to have something, an action you would take. Regulatory oversight is going to be incredibly important to make sure that all these things are done well. And finally, there needs to be some kind of financial responsibility model so that if 50 years from now, 100 years from now, or if after the project stops, if anything goes wrong, that there's money in the bank to pay for it. So that's one of the institutional challenges that needs to be grappled with. So now I'll just hit on a couple of the things. So the first thing is when you put CO2 underground, it's not going to be a gas. It's going to basically be a supercritical fluid, which basically in practice is a sort of liquid-like density with a gas-like viscosity. So, and the density shown by this red curve will be about 2/3 the density of water. Okay, so it's going to be buoyant, but it's not a gas. So when you think about a mental model, think about it as a sort of a slippery liquid. Okay, so it's in the reservoir, so you're injecting it into this sand body. Well, what does it really look like? Is it some big bubble, that's sort of waiting to escape? In fact, it's not. We now can do microtomography images using the light sources, the Department of Energy light sources, and basically we can make real pictures of what the CO2 looks like in these rocks. So the red are the rock grains, the green is water, and the dark blobs, that's what the CO2 looks like. And you have to appreciate the scale of this. So this whole thing is 2 millimeters. So you can see that the gas is actually very, very tiny individual basically blobs of CO2 that are connected, but they're connected through a very tortuous pathway. So if you have some kind of penetration into this, you can imagine that there would be a great deal of frictional resistance to moving that gas quickly out of the subsurface. It also shows why it's kind of difficult to put it in there, because you actually have to push the CO2 so that it can get in all these individual pore spaces. Okay. So I want to talk now about what is it that keeps the CO2 underground. Well, the primary trapping mechanisms I already alluded to is you have to put it beneath seals. I'll say what seals are in a minute. But there's some sort of longer-term processes that are also important, that CO2 dissolves in the water. It can be trapped by capillary forces, which basically immobilize the CO2. And eventually, it can also be converted to solid minerals, carbonate minerals, calcium carbonate, magnesium carbonate. And then if there's organic material, it can also absorb to the organic material. But the most important one is seals. So I want to say a little bit what are seals. Basically, seals are rocks made up of very, very fine textured materials, nano-sized particles, clays. And these are highly compacted together. And that does two things. It makes it so that it's really difficult to push fluid through it. So that's called low permeability. So it wouldn't matter what kind of fluid you had present. It would be just difficult. You'd have to have a huge pressure gradient to push fluid through it. But the second thing, and the most important, is that these very, very fine textured materials provide a capillary barrier, or basically a membrane seal, to the secondary fluid that's called the non-wetting fluid. So these clay minerals want to be coated by water, and it adheres very, very strongly to the surface of those. And CO2 is the second phase, and it doesn't want to attach itself to the surface of the rocks more than water does. So basically, it creates a membrane. So you can flow water through it, but unless you have very, very high pressures, you can't get the CO2 to flow through it. So it's this double mechanism that makes it so that CO2 could be retained underground beneath these seals. And it's basically what's primarily responsible for the virtual existence of natural gas reservoirs that are found in nature. So that's what we're looking for in a seal. I mentioned that there were secondary trapping mechanisms, and this is just sort of an illustration of one possible example of how these secondary trapping mechanisms would evolve over time. So you can get dissolution of CO2, you can get mineral trapping, and you can get this capillary or residual trapping. And the idea is that after 100 years or 1,000 years, much of the CO2 may actually have converted to these other forms that are basically immobilized in the subsurface. And why this is important is that we don't want to have to worry about these things forever. If you put CO2 underground, you don't want to be 1,000 years from now just as worried about it as the day you put it in. And that's why these are important. Monitoring is extremely important. None of these projects will take place without monitoring, and there's a whole bunch of different technology that can be used for monitoring. I'm going to give you two examples. One example will be the monitoring technology that's basically used to look at where the CO2 is in the subsurface. And the second is monitoring technology that can be used on the ground surface to detect any leakage. So this is actually a map, or it's actually two different maps. It's on the top are cross sections through the Schleifner plume, and on the bottom panel are map views of where the CO2 is. So on the left-hand side here, This is what the subsurface looked like before any CO2 was injected. And this is using seismic imaging. So basically, you propagate compressional waves or shear waves through the subsurface. When it encounters the CO2, there's an impedance contrast, which causes reflections. So it's standard technology, but turns out to be quite exquisitely sensitive to the presence of CO2. So this was before any CO2 was injected in 1994, and the image on the top now is this cross-section through the Earth. And you can only see a couple of features. One, you see a reflection near the top. It says top of the Utsira sand, so that's the top of the storage reservoir. And you can also see a reflection on the bottom. And looking down at a map view, don't see much of anything. So in 1999, 3 years after they started injection, they did the first image, and all of a sudden there are all these strong reflectors that are showing up. And basically those are indicative of the presence of CO2, basically where it is located in the subsurface. So in this cross-section, you can see that it's sort of spread out in thin little layers within the storage zone. And here you can see the size of the footprint of the CO2. And this has been done repeatedly. This last image is shown in 2002, but they do this now every couple years, and I just didn't show those. So basically, it shows us that we can tell where the CO2 is in the subsurface. Very importantly, if you look at the top of the storage reservoir, you can see that there's not evidence that CO2 has escaped out of the seal. So this is proof. When I said that Schleipner is going very well, this is the kind of evidence that's used to show that, in fact, the CO2 is staying underground.
Is the dark the injection at the end of the well?
Yes. This is the injection well location. Yes. Right. So it was near the base of the formation. Yep. Okay. So surface monitoring. It may be that either there would be a requirement or it would be desirable to have some definitive proof based on surface monitoring whether CO2 was leaking or not. And it turns out that the people who study natural carbon cycling between the atmosphere and plants and soils actually have developed a whole suite of technology that's extremely sensitive and that can be used to detect CO2 fluxes from the surface. So basically, all of these are being borrowed for the application to this problem. And there's actually an experiment that was set up in Montana where there was a long well, 100-meter long well that was drilled very close to the surface, 1.5 meters below the surface. CO2 was injected into it and allowed to leak out so that people could test out whether these various instruments were working. And here's a picture. You can see the field where this experiment was done. The blue flags show the outline of where the well was. Here was the injection system. We very carefully controlled all the injection. And on the right-hand side are some of the monitoring techniques that were used. The first one is called a flux tower. And that one can directly detect fluxes over a fairly large footprint. Here's a little device, kind of like a cookie cutter, that you can go and sort of raster over the surface and measure fluxes. This is very, very sensitive. You can measure soil gas. And there are also studies to look at plant stress. It turns out, actually, as a detection sort of diagnostic, plant stress is probably going to be extremely valuable. And you can do this based on in plains, or you can do it on the land surface. So basically, when CO2 is in the soils, the plants become stressed. Even if it's not visible to your eye, the spectra, the reflectance spectra off the plant changes, indicating that something is different. So this is the kind of monitoring that can be used. Okay, so quickly, because I'm running out of time, storage capacity in the U.S., so this is just one example, that detailed studies have been done of oil and gas field sequestration capacity, saline aquifers, and coal. This is just the map showing where there are saline aquifers that are deep enough, which is typically greater than 1 kilometer, to potentially store CO2. And so you can see in the U.S. there are lots of them, and there are actually numbers on capacity, but they're just big numbers, so they don't really mean much. So a simpler way to look at this is to look at the ratio between the sequestration capacity and the amount of emissions, for example, today. And these are actually 4 or 7 different parts of the United States. So this is sort of the Dakotas. This is the Midwest around the Illinois Basin. This is sort of the Ohio, Iowa area, West Coast and Alaska, Southeast and Southwest, and Montana area. And together, these pretty much cover the country. And so the number on the left-hand side is basically, again, the ratio between the storage capacity and annual emissions. And if you look, for example, at, well, let's pick one, CCARB. This is the southeast. This includes the Texas Gulf Coast. You can see that the low range of the estimates, there's a couple hundred years capacity for storing CO2. If you look out in the west, very large capacity, over 1,000 times. So, yeah, so there's a lot in some areas. If you look at other areas, say in the southwest, doesn't look like so much. Low end of the range, maybe about 50 years of storage capacity, probably not enough. They would need to export CO2. So the story is that there's some place with a lot, yeah, and some place not so much.
Average it out over the whole Earth or whatever, and look at how many coal is there. Do we have enough storage to take up all the coal?
Yeah, the estimates are in excess of 10 billion tons, 10,000 billion tons, 10,000 gigatons of CO2 storage capacity, which would be sufficient for hundreds of years of burning of coal. Yeah. For fossil fuels, it's about 5,000. Yeah, I mean, it's always hard because it's which fossil fuels is that? Is that all of the oil shale? Is that all of the, methane hydrates? But 5,000 is sort of typically the high end of the number that people think are.
There's about 100 years of coal, I think, for recent updates in the United States at current rates. So
Yeah. Yeah. So. Yeah. I think that we would run out of fossil fuels before we would run out of storage space. But that's not to say there are plenty of areas where there's not storage space. And, China may be one of those. India is certainly one of those. So it's very, like any resource, it's variably distributed. Okay, so what could go wrong? Release pathways. We can't just say, oh, it'd stay down there. We have to consider what could go wrong. Well leakage. Every time you put a hole in the ground, it's a potential leakage pathway. People could make a mistake and not characterize the site correctly. You could have excessive pressure buildup. If you inject at too high a rate, you can actually damage the seal. You can fracture it. So those things could go wrong. In terms of wells, the panel on the left here shows the distribution of existing wells. Very, very high density in parts of North America. So leakage through existing wells is a concern. Okay, so what would happen? What are the potential consequences? This is a list in my order. This is nobody else. Other people might have a different order. Number one, I think worker safety. We know from oil field operations that number one thing is people who are workers are the most exposed. And so just like oil field operations, worker safety is an issue. Second, groundwater quality degradation. Even if CO2 doesn't get into an aquifer, there is a potential for brine migration. So not only do you need to make sure that the seal is good to retain CO2, but you need to understand the hydrology well enough to know that, in fact, you won't have brine, salty brine, moving up into a drinking water aquifer. Resource damage, thought of primarily in the context of damage to hydrocarbon resources. If someone doesn't want CO2 in their gas field, it gets there, they're going to be unhappy. Ecosystem degradation. If you have CO2 leaking out, we know it kills vegetation, kills fish, so that wouldn't be a good thing. Public safety, if you have, some kind of well blowout and someone's unlucky enough to be near where that is, or if you've got a pipeline leak, somebody could get hurt. Structural damage, if you are injecting at too high a pressure, you could have microseismic events. You can have inflation of the land surface, even in the absence of that. And then finally, release to the atmosphere. So again, I think that you can design projects. These are manageable risks, but people shouldn't be blind to the fact that there are these potential risks. So one of the questions the public has is, well, what about catastrophic releases like Lake Nyos? This was in Africa. There was a lake that had a huge release of CO2, about 250,000 tons of CO2 was released within a short time, few hours. And it created a big plume of CO2, which then flowed down a valley and killed thousands of people. It was absolutely tragic. And so we get lots of questions. Well, could this happen? Well, to give a perspective, that number, 250,000 tons, is a quarter of all the injection into Schleckner for a year. So the idea that somehow you could get a release this rapidly, it's just very, very difficult to imagine. The other thing is that the mechanism of the release was completely different. Lake Nyos is a stratified lake. That means that it doesn't turn over. Typically, lakes, circulate between the surface so they can release their gases, and then it gets cold, and so that water goes down to the bottom. And so they're always well mixed. But there are certain very deep lakes. Crater Lake is another one that are stratified. And what happened is this is in a volcanic region, and there were natural releases of CO2 into the bottom of this lake. This lake then turned over, maybe because of a subsurface landslide or something. And once you lift up a little bit of that water that's got CO2 in it, if it's saturated, all of a sudden the CO2 comes out of solution. It becomes self-enhancing, and it just just like opening, your soda bottle. If you shake it up and open it, it makes a big mess. So anyway, so that's the mechanism. So I don't believe that any kind of release scenario like that is credible for CO2 storage, but again, we need to be aware. So anyway, I'm taking too long, but I guess I'm going to just sort of jump to this. Are we ready for CCS? I think in oil and gas reservoirs, absolutely. We know how to do this. It's done today. Saline aquifers, we still have more to learn, but certainly we're ready for large-scale demonstrations. And in coal beds, I think there's a lot more science. That very foundation of the pyramid needs to be further worked on. Costs, basically, the range for costs of CCS is in the range of $20 to about $70 per ton of CO2 for the kind of systems you would anticipate. This is based on IPCC 2005 data. There's McKinsey just did a new study that sort of verified this range for projects that are done after the learning curve has been achieved. Their range was about $39 to $58 per ton of CO2. However, very importantly said, the early projects are going to cost a lot more, in the range of $77 to $116 per ton avoided. So these numbers provide good basis of comparison to other CO2 mitigation technologies. Another perspective is how does it change the cost of electricity? And there have been studies to look at this, but sort of the simple bottom line is that electricity production costs, not retail costs, but production costs will increase by something from 50 to 100%, depending upon the technology. So, significant cost increase. Department of Energy is doing a lot of research in this area. Their long-time goal has been a 10% increase in cost. They're likely to change that to about 35% increase in cost, so, which is probably in sight, given the innovation in new capture approaches. So anyway, just to go back to this list, CCS can result in 20% of needed emissions reductions over the next 100 years. Well, potentially yes. The technical potential for CO2 capture and storage to achieve this is probably real, in my opinion, based on the discussions that we've had. Are we going to be in trouble if CCS doesn't sort of pan out in terms of not being able to meet mitigation targets, particularly when we look worldwide? Probably. And we have a lot of coal in the system, a lot of other fossil fuels in the system. At the very least, CCS will make all this easier. All of the components are available today. We just need to put them together. In part, that's true, but I don't think it's quite that simple. The capacity to do CCS projects isn't there today, and the confidence in terms of investor confidence to do these projects isn't there today. So, it's sort of yes and no at the same time. 30 years of experience in oil fields. Yes, we do have this. We know how to put CO2 into oil reservoirs. I'm not at all worried about that. But for saline aquifers, which have the biggest potential, we need more large-scale demonstration projects to show that we know how to pick good storage sites. Just do it. I mean, if somebody said all new plants had to have this today, I think that that would be very, very difficult. But we're certainly ready for large-scale demonstration projects. So, I think if we're building new coal plants today, we should make them demonstration projects. And so, in that sense, we should just do it. Okay, hype. CO2 is extremely expensive. I say compared to what? Compared to living with the risks of climate change. No, I don't think it's too expensive compared to that. If you look at the cost of power generation with CCS compared to solar today, it's still considerably less expensive than that. Though, of course, there's huge innovation taking place in solar PV today and solar thermal, all of which is fantastic. But I don't think you can argue that it's simply too expensive to do in light of the risks that we're facing. Environmental risks, unmanageable, unacceptable. No, I think if you do these projects carefully, that they're manageable risks. CO2 will leak back to the surface. No, again, not if done carefully. And then the final issue is institutional barriers. There's some concern that the barriers are simply too high. And I think this is really a big issue that, and I'd like to just sort of wrap up with those. So clearly CCS won't be done until there are policy or other or regulations to limit carbon emissions. This is not going to be done on a voluntary basis. We need to deal with the institutional framework for long-term liability. My favorite approach is some kind of trust fund that basically you buy into. So for every ton of CO2 you put underground, you contribute 5 to 10 cents, which should be enough. That builds over time and basically provides a resource for any needed remediation far into the future. Legal framework for putting CO2 underground into pore spaces. We have a very arcane set of laws about mineral rights, property rights, pore space rights, water rights, all of which are very complex, vary on a state-by-state basis, and someone needs to sort out who owns the pore space, particularly in saline aquifers. This has been done in Wyoming. They decided they belong to the surface owner, which is probably a good answer, in my opinion. We need regulations for storage. Basically, how do you select a site? How do you monitor the site? What are requirements? What are performance specifications? I mentioned that you can inject it to a higher rate. Well, those are their standard regulations that apply for oil field kind of projects today, but we need to have those same kind of performance specifications for CO2 storage projects. Carbon trading credits. There would be a lot of interest probably in doing these projects if you could trade the credits for that, and it will have to be decided whether these would be eligible, and if these are eligible, what are the rules under which CCS projects are eligible. Another important area is CDM, the Clean Development Mechanism. It would be possible to do some of these projects in developing countries if a methodology for CCS could be approved under CDM. That hasn't happened yet. As a matter of fact, they were rejected. Two projects were rejected, or two methodologies were rejected. And then finally, public acceptance. We're not going to do this if people don't want it, either philosophically or if they don't want it in their backyard. And there's an ongoing discussion about this. I think we've seen a lot of movement from the larger environmental groups are very supportive of CCS. They think it's very important. NRDC, Environmental Defense Fund. Just a couple weeks ago, Greenpeace, World Wildlife Fund came out and said we should do demonstration projects on CCS, which was actually a big change of opinion on their part. And I think in areas where people are used to oil and gas operations, this will not draw real concerns about public acceptance because people are used to the idea that you can inject things underground. I think in those areas where it's a completely different thing, I think that people will have concerns about, damaging property values and so forth. So some areas will be easier to do this than others. Anyway, so those, I think, are some of the ongoing issues. I was asked to sort of wrap up with that, and I think the institutional issues are really important. So, thank you.
I have two questions. The first one is regarding the separation of, using pure oxygen as an oxidant in the... What if you dilute the gasified fuel with already separated CO2? Can you use that in existing plants without having to go to high temperature or newer materials?
Yes, exactly. They call it recycle, and yes, that's exactly one of the approaches that's being considered. Yep.
Would that be the most cost-effective approach?
So far, that looks very good. Yep.
Okay.
Yep. I don't know what other approaches to that have been considered, but I know that's one that's very of interest. Yep.
The second thing is, another thing that is mentioned is the pipeline network that is required to be built to transport this, of the order of the existing world's pipeline infrastructure every year for the next 10 or 20 years. Do you see that as being feasible with the land acquisition and other concerns on that front?
Yeah. I think people have used this analogy that if we do CCS on a really big scale, it's going to be equal to the volumes of fluid we deal with in the oil and gas industry. And that's true. There's no question that that's true. But I don't think we would want to replicate that infrastructure. So in an oil field, for example, you might have hundreds or thousands of wells because you put them in because you want to get every last little bit of oil out. And then you have to have your whole pipeline connecting network to deal with all these wells. Similarly, in gas fields. I don't think you would design a CO2 storage project. You're going to minimize the number of wells. I think you'll design your big transmission lines to have economies of scale. So every power plant wouldn't go and build their own infrastructure. They would negotiate together, and it would be more cost effective and help deal with some of those issues. Nevertheless, siting pipelines is a big issue, and but I don't think we need to think of so many pipelines as we do for the oil and gas industry. I think also that in terms of the distribution side, it's a much simpler problem. Yes.
I have two questions as well. Can you explain a little bit more on IGCC? Sorry. On IGCC, the mechanism for doing the pre-combustion separation, and then on IGCC, you showed a 10 to 15% energy hit, but you also said that hydrogen is produced. Can that hydrogen be used to create energy and decrease the energy loss, or is that already built into the numbers?
It's already built in, so that 10 to 15% is sort of a full life cycle, energy assessment. So basically, what you do is you oxidize coal under reducing conditions. So you don't allow the combustion to go to fully combust, and so you end up stripping hydrogens off the coal. And then you also end up breaking down some of the long chain, organics into carbon monoxide. So you can use both carbon monoxide and hydrogen as a source of energy, or you can decide that you want to react doing something called a shift reaction, where you react CO with water, H2O, and then you produce more hydrogen, and then all the carbon goes to carbon dioxide. You can't get away from the energy penalty because you still have to separate the CO2 from the hydrogen in the end, and that's where your energy penalty is coming.
How much are you counting on the hydrogen? If you didn't use that hydrogen, you just let it vent, how much worse would the energy?
You need the hydrogen. Yeah, I mean the hydrogen is then what you use for combustion. So you combust either hydrogen and oxygen, or hydrogen and carbon monoxide with either oxygen and air. So yeah, so that's your energy source. So basically you're kind of making a gas. So you convert the solid coal to a gas, which you then combust to, or run through a gas turbine.
So you mostly covered geosequestration in this talk. There've been some recent technologies to, let's say, mix this with lime and convert it into cement. I think Calra is doing it. Or there are efforts to actually use this as a feedstock for maybe ethanol production. So what do you think are the promising technologies for sequestration?
Right. So the question is CO2 reuse. Obviously, everyone would way prefer to do that. And the work in terms of mineral carbonation or making cements, there's a company which you probably met with, and I can't think of their name right now, who's working on using CO2 to make cements. So I think those are great things. But if you look at the scale, I saw a fantastic statistic, well, interesting statistic, that if you look at the whole chemical industry, that the scale of the CO2 compared to that, if you look at mass of CO2 compared to the mass of chemicals produced in the chemical industry, it's a scale of like 100 to 1. So even if, all these feedstocks you could start making from CO2, it still is just a drop in the bucket. The only thing that compares at scale is obviously fossil fuels, which makes sense because they're derivative from fossil fuels.
Okay.
So
another question: how does the production of CO compare to CO2, like worldwide, as ratios? And are there some sequestration techniques? Is it big enough that it warrants different sequestration techniques
for carbon monoxide?
Yes.
I don't know the answer to that. I don't know, which industries are producing, they're probably using the CO.
I think the iron industry, the steel industry produces CO, which is why I was curious.
Yeah, sorry, I just don't know enough about that.
I was wondering what you thought about some of the other ideas to consume CO2, like algae. I mean, obviously that's not solving the net problem if we then make oil and burn it, but what are your thoughts on that?
Yeah. Again, the idea is appealing because, again, reuse, algae, a lot of potential reuses for algae. I think, again, it's a question of scale. The amount of acreage you need to deal even with a million tons of CO2 is huge. And I don't have that number, off the top of my head right now, but the scale is absolutely gigantic. There are also water use requirements. You also have to do this in a place that's hot. There are also challenges with maintaining the culture. So I think they're interesting. I don't think we should be. I think it's way too early to be discouraged. I think they're really important research problems. In terms of whether they'll, really come to fruition as a way to deal with this giant amount of CO2 we have today, I'm kind of skeptical. But in the future, we can imagine a world where we have way less CO2, but there might be, that we still might have some CO2. And in those cases, if it was 10% of what it is today, maybe, these ideas really, have a lot of merit.
Follow up?
I guess the overarching question I had was just this perception as being somewhat of an outsider to the CCS community now, that the process has stalled in the last few years, that it doesn't have the momentum that people thought it did a few years ago. And I'm wondering how true that is, and maybe there is a lot of movement, it's just more behind the scenes in committees and such now.
Right. Yeah. Well, I think what you're referring to is there were a lot of really large projects that were announced that have stopped, and there are the BP projects, the DF1, which was going to be in the UK. There's DF2, which is sort of in limbo. Actually moved probably to the Bakersfield area. So there were those, and then there was FutureGen, and yeah. So I think that the Sask Power project. basically, they just all ended up costing more than people were willing to pay, I think, at the end of the day. And part of that was just because this huge escalation in capital costs that we've seen with everything. So it's not so specific to CCS. It's just concrete and steel are very, very costly. So those things happened. I think that there's a lot more quiet work that is being done. I think people have gotten tired of announcing projects and then, pulling back on them. BP has, announced the movement of his project from Carson to the Bakersfield area. I think that's encouraging. The Australians are very aggressive with planning for large-scale demonstrations. The SaskPower has re-announced plans for their project, again, scaled back. So people are being somewhat less ambitious. And I think there's, until there's regulatory certainty that you're going to have to pay for carbon, I think it's not going to have such an incentive for people to consider these, multi-billion-dollar projects, which is what they are. It's a lot of money.
And that's no different in Europe, where you might argue there is a little bit more regulatory certainty, even though it's short term right now.
Yeah, I think that's true. But the Vattenfall project is going ahead. So things are moving. It's just not quite as fast. Certainly, the community of people is growing. I think what we've seen is a lot more interest by the investor community, a lot more interest by the insurance community. So it's sort of a growing group of people, but certainly it would have been nice had more of those early projects gotten off the ground. Because to me, the most important thing is real projects, real data, transparency, and experience. That I think that's really what's needed.
So we're running out of time. Actually, we're 20 minutes over time. So one last question.
Hi, well, I have a few questions, but let's see, I'll just pick one. Well, the first one is, so there's two different ways of doing IGCC, one of which extracts all the CO2 from the system, and one of which extracts, I'm not sure what the number is, like a half of it or something like that.
Right.
Is it correct that the one that extracts all the CO2 from the system requires the same high temperature materials or processing that the oxyfuel appears to need if the CO2 feedback thing doesn't work?
I don't know. Yeah, sorry. I'd like to give you an answer that I'm more a specialist on the storage side, so I really can't tell you. And the issues about optimization of to do the shift or not do the shift, I haven't seen a lot of publicly on that. It might be that that's being done more by companies who see them as providing those products, the GEs and the Siemens and the so.
It seems like it's completely politically motivated, and as a result, they're just trying to match the CO2 emissions of natural gas power plants. So they do the halfway one.
Right.
Yeah.
Right.
Can I ask one more question? Okay. I look at these cost numbers, and I can't make them work at all. And I wonder, is the expectation that the pipeline lengths taking the CO2 from the power plants to the sequestration fields would be like the current rail links between the coal mines and the power plants? The reason I ask is because the average rail link in the U.S., average distance coal gets moved to a power plant, is 628 miles right now in the U.S.
Yeah.
And I was kind of actually happy to see, hadn't seen this before, your Dakota to Canada, I've forgotten the name already, link seemed to be on the order of that size. So that's nice, because it means that somebody's got experience with moving CO2 over that kind of distance.
Right, and actually the people who, Kinder Morgan, who owns most of the CO2 fields and sells CO2 to all the people for enhanced oil recovery, there are over 3,000 kilometers of CO2 pipelines in the United States. But the economic analysis typically that have been done restrict the pipeline length, like the McKinsey numbers. If it was greater than 200 kilometers, it wasn't included in their analysis. And I think down the line, if this is ever really done in a serious way, people will look at optimal locations for power plants in relationship to transmission lines, sequestration sites, trains to get coal to places. So, I picture ever just replicating the current power generation system we have today. And that would be so unoptimal that.
We have to stop, but I did want to say before we close out that there will be another CCS talk in about 2 weeks by a professor that I'm sure Sally knows well, Julio Friedman from Lawrence Livermore. I believe it's Monday the 3rd, but we'll give you details on that, so you'll have a chance to ask follow-up questions. Thanks, everyone, for coming.
Yeah,
and
thanks
thank
for
you,
coming.
Sally.
Sorry to be so long.